Welcome everybody into my channel. This is the video 2 of the computational chemistry, and in this video I would like to talk about the concept of potential energy surface. The potential energy surface is a central concept in the computational chemistry, and a lot of the problem and a lot of challenges mathematically involved of the potential energy surface. And what is the potential energy surface? Potential energy surface is the mathematical or graphical relationship between the energy of the molecule and its geometry. And it means that in the molecule we have a lot of the geometry, and its geometry will have the energy, and it's called of the potential energy surface. And when we do find the potential energy surface, we will use the spherical equation, but the solution it cannot guess the exactly of the energy of the spherical equation. So we need to use the ball of Oppenheimer approximation. And in the bond Oppenheimer approximation, we will be say that the nuclei are essentially stationary compared to the electron, and it will be much easy to the solve of the spherical equation, and we just focus on the electron energy in other nuclear deposition energy later. So we will come to the next slide. In this slide I talk about the perspective of the potential energy surface. Normally consider of the molecule with the two atoms, and for the simulation we will can represent the atom like a bonds and the bond like the string. And in the picture we can see that this is the ball, and we can connect this two ball in here. We can connect this two ball to the cloud, and we can set it in the far away, far together. And this is the equilibrium position when the is in the S less when equal to 0, and this is the when we compress the two atoms view in 3, and we when we set it far away, and also in 3 also, and also in 3 also, and this and energy of this is called the potential, and the potential is the quadratic equation for long distance. The distance is turn up we compress, and distance when we change our weight. This is the chart. I will draw again of this model. You can see it's not so beautiful, but we can see that. You can see this is the two atom A and atom B. Okay, in the normal we can normal of the molecule, we will get the A energy less 0, because we can we do not affect a lot of anything in the molecule, and this is the position when energy is equal 0, and when we compress this and we will check this, the energy will be in D in here and in D in here. And the energy in this situation will be called PES. Yes, this is the very symbol model to represent the potential energy surface. Actually, the molecule behavior similar to in the real time, but we have the some different of the behavior of the molecule. Uh, you can believe remember of the Heisenberg uncertainty. We cannot uh, have exactly amplify momentum in the position. The Heisenberg will be try that delta is the mobility delta position, and delta p is the momentum. Greater or equal than reduce Planck constant divided by 2. This means that in the energy level, we cannot find exactly of the position. It means that we come to the chart below. It means that in the energy of the zeros, the atom cannot stand here. I cannot stand here. It stand in here. It stand might be in here, or might be in here. It might be in here, and we call that the vibrational level. The second, you can see, need the equilibrium length, create the potential energy length Q for the magnetic bond and string model, and all the three molecule is described very well by a kinetic equation that the simultaneous oscillator. However, the potential energy derived from magnetic Q2Q as we move away from QE is being tested. You can see when the energy in need of the QE, the error from the ideal kinetic Q in loss, and I think it's the best derived for the energy, potential energy. But we can go far away. You can see the error this Q and the kinetic Q is very different. And this is the true molecular potential energy Q, and this is the kinetic Q for the ideally. You see the two by when the atom in the molecule is behavior in different from the ideal kinetic Q. Okay, let's move to the next slide. Next slide we will to illustrate of the difficult of the model, and we use very simple molecule in the real time. This is the water molecule, and you can see we have in the water we have the two of the parameter for this. We have the angle, and we have the oxygen and hydrogen bond length. And for that, we need to chart the 3D chart for the price of the potential energy surface. And you can see we can the price of the energy and with energy when energy in here, and it's the minimum energy is for the Q1 and Q2 depend on energy, and you can see energy in here is not equal zero, not zero at all. Okay, really in of the different difficult of the model is more difficult. We to the SOF. It is SOF. The bond length of hydrogen and oxygen flow is not the same, is not equal. And we also have the SOS and angle of the molecule. And for us, for energy, the beside of the Q1 and Q2, we need to another parameter as for the oxygen and flow. This is the Q3, Q2, and Q1. And for this chart, we cannot draw, we cannot loss of energy again of the parameter of the Q1, Q2, and Q3. And if we go into the 3D plots, and so it's called of the hypersurface. And for us, how can we research how we can represent energy of all the Q1, Q2, and Q3? It's very difficult. And for us, we have the solution. We will to get the some slide, and some slide is line in the chart in here. And for this slide, we turn off the 3D plots into the 2D plots, and we get the minimum of the energy in the event of the derivative on the energy divided to derivatives delta Q is 0. For the water, we will be the boy when the derivative is divided to derivative Q1, and the energy divided to derivative Q2 is equal 0. It means that we have the three loss. You can see the three loss of the quarter, and we have the surface again up to Q1 and Q2, and we test the slide here, and we could test slide here. We just have a energy L Q2 is the angle of the quarter, and here we will turn it into here to the first chart, and second with that to the slide 2. Slide 2 here. We can see it here. I will to illustrate your eye here, and you can see it here, and you have the second chart. And for the second chart, how we can identify of the minimum identify of equilibrium is depend on here. It depends on here. This is the minimum point, and this is we will use here derivative of energy again of the derivative again of the Q1 plus derivative E divided on derivative 2 plus 0 equal 0. And when we be slide for that, we can we can hold on of the auto the two geometric parameters control to the reduce of the harder of the difficult point of view. So of geometry minimization. For example, when we hydrosurface of the hydrogen oxygen flow, you can see we have the hydrogen flow, but in this chart we cannot see the hydro of the molecule. We just see the boiling of Q1 and the Q2 of the boiling of oxygen flow of vessel. And because why we can do like that? Because maybe the hydro might be the same for the calculate, and this is because that it lasts or decrease the potential energy. But when we calculate the potential energy with the best hydro corresponding of the order to both two parameters, the geometry is calculated will be the full optimized, and we will come back into the session 2.4. and we call that the last potential energy surface. This means that when we do when we get slide and we get to of a 3D slide, we can fix up the one parameter and we get the sound to and we minimize equilibrium of energy then again of the author parameter. But we can get the real of the potential surface of the L division surface. This is the end of the video too. Until maybe if you have the animation, we could be released. Please comment on it below. Thank you for attention.